But yeah, he's like obsessed with it.
I know.
He's like, guys, this is the future of computing.
Dude, I think
Over
he
and over.
just likes the idea of it because it's going to be super hard.
It already is. Like, I have like no clue what code even looks like to generate something. Like, the most impressive thing for me was like the like realistic depth perception. So the issue with VR goggles is that they can't replicate depth perception because the screen is at like a static distance from your eyes, so your eyes are at the same focal length for the entire session, which is what leads to eye strain. But the Magic Leap has a front-facing camera on the goggles that like tracks your eyes, so it can tell where you're focusing, and it'll actually like bring that part of the augmented reality in focus. Wow. So it's really cool. So you can like, so we're in like a room, and I put like a slide down, so it's like from like there, and slide like down my face. I dropped the ball at the top of the slide, and then I watched it like come down, and it looked like the different parts of the object were coming out. Like, wow. Yeah, it was. Oz tried to pitch me on like the grand vision of like this is what like
I got that pitch too.
life is gonna be like. I could see that, but the fact that it took them like $2 billion and like a decade to get to this, which to me like isn't really consumer ready. Like, it's kind of.
It's the same thing with like Oculus and stuff. It's like this is cool, but it's like we're not there yet.
Yeah, it's
like,
way more impressive than any other VR, but still.
Back in 10 years.
Yeah. And the other really impressive part is it's all self-contained. So like you just like the battery, everything. It's, you don't need like
nice.
PC power. So.
That's kind of amazing.
Yeah, like I mean,
thought you'd be tempted to something.
You can like take it out in the street and just use it, and then like figure out that. I'm just impressed they actually got this. They're looking. Yeah.
Did you want to do? Sorry.
Oh, sorry. Floyd Hub.
Floyd Hub.
Yeah. So Floyd Hub is like you can they were licensed. Okay. So they have. I'm actually subscribed to the newsletter.
Yeah.
Hang on today.
It's like Heroku for deep learning.
Oh. It's a very good description.
Yeah. So I was actually like your whole write up on like the curriculum, and, like why transition. You put it on Slack.
It's on my website too. That's how
cool.
That's how he contacted me. It's a friend of mine who works there. I saw on the website and he read that thing.
Nice.
I was like, oh, do you want to write a blog post on our blog? With 25,000 viewers.
What blog post do you?
So I posted that curriculum on my website.
On your
website? This is how I have a post about like I learned how to code like books I read the past one. Right. And then there's a bit at the end. It's like, here's what we did for MLE Paper Club. Here's Paper Club. I mentioned both of you. And then here's the curriculum for like machine learning. Blah, blah, blah. And it's all of that. It was like, you guys, if you want to talk about like, welcome in. He was like, if you wanted to talk about your course, or if you wanted to do like any other blog post or project, like we work together and make that a post.
I mean, do you want to just repurpose your curriculum?
Yeah, I'd be down. Make YouTube videos of these recordings. I'll clip out all this first bit. Yeah, I don't think anyone would, but like having the content there to like browse is
We get like a generative model like
we met a billion times. You guys want to get started?
Cool. I don't know if we've got
we don't. So I'm the second partner.
Yeah.
Let's get used to saying.
You work at Social too?
Yeah. So we started like half a year apart from each other.
So I saw you in the second.
Yeah. he moved here, and I'm staying remote.
Okay. Gotcha.
I'm just visiting for like 2 weeks.
Cool. Well, I'm visiting too. I live in Denver. You live in?
But it's not worldwide.
Yeah, dude, my GRU CM thing keeps getting more like reviews.
Really?
Like every single
Really?
week, yeah. It's pretty great. I think it's like second on Google now.
Dude, Medium does a really, it was a Medium post, right?
Yeah.
Medium does a really good job of like floating our content.
Yeah,
I still get a ton of views on one of the first posts I ever wrote. Multimodal question answer.
It's weird the ones that you get a lot of reviews on or views on, right?
I can see that theory. I feel bad because the conclusion is basically like they're the same.
It's just gotta guess.
Well, I guess like I mean, the conclusion is that they're the same performance-wise, so you should be the best in space or something like that. But you.
All right.
That's not even yeah.
Let's get started. We got like 18 sections-ish to get through.
Oh my god, yes.
So Bartosz, you want to start us off with the intro to the regression? And let's try and make the transitions like pretty quick too.
Yeah.
Also, conveniently, we're going in the circle in this direction.
Okay, cool. No, no, nice.
Second Bartosz, are you just hanging out?
No, yeah.
Okay.
Hanging out. I was just informed that this thing is a thing.
Yeah.
Do you have like a background, just quickly, do you have like a background in ML or anything? Or just,
Not really. I must be trying to learn. That
Nice.
was one of the few things I almost no idea about.
There are many things.
I don't know.
Yeah.
Way ahead of us.
Do you have any goals in particular? Like, would you want to do this more, or do you have an idea of like how projects you want to take on?
I'm not sure. Like for now, I would at least like to know some of the very basics, so I just understand what I'm talking about when doing this. Like, for example, I have absolutely no idea how any of our modeling stuff works. There are matrices and they get multiplied. It's about the extent of the image.
You are not. Soon we may be doing SPMs. Okay, so linear regression. I'm not sure I have to go to perspective. Like, okay, here's what linear regression is. Yes, fitting models. This is us looking behind the covers. Okay, how do they actually do the things we do? And yeah, so basically, like, it's why it's called linear is because, like, okay, your prediction is a combination of like a bunch of factors and multiplied by each of your features, and there's also like a null term, which like just gets added to your thing. I was confused about the null term in the later section because it was like, okay, but like, if you make a prediction, like, okay, why do you multiply this null term by? And then people told me, like, okay, so like usually when you multiply matrices of the features, the weight for this thing is 0, and it's just sorry, the weight for this thing is 1 normally, so it gets added effectively then. And yeah, that's like,
Yeah, there is some confusing stuff about that later. Like,
no,
at
so
one
like
point he instantiates a polynomial regressor with like the bias term. The bias is false.
Yeah.
And I was confused a little bit about the bias term versus the intercept. Like, are they the same? Are they different?
Yeah.
that I'm not sure about yet.
I thought with a polynomial you can like without any interest, like you don't need to specify a bias because there's something like that.
Yeah,
That makes sense.
I think hold on, the
Sorry,
linear one is
that's
that.
fine.
Yeah, it's actual science. It's still alive.
Oh yeah, are we recording? Yeah, okay. And yeah,
I think
so
it's fine if we're working with that.
the nice thing was like, just if you remembered a bunch of a bunch of stuff about going from just here's a for loop essentially in the form of an equation and going from that to like matrix notation. That's like the very first workers are super nice to refresher on that because then you're like, oh yeah, well, okay, that's how matrices work, and that makes all the other notation in the chapter way more efficient. Which is one thing, and the other thing, like, yeah, so the one thing I mentioned, like, okay, so x is the instance of the feature vector, and the x0, which is like the 0th feature, not a real feature, that's always set to 1 because that makes the bias term. I mean, sorry, I'm not sure if it's called the bias term. It's the, well, it's called.
Is it part of the like trainable parameters?
Yes, like so if you look at the equation for 1, right? There's theta 0, and I'm not sure what theta 0 is actually called.
Oh, are you into
Theta 0 is the coefficient for
Yeah, coefficient for the feature that doesn't exist, which you always multiply by 1.
Yeah.
That is the offset, but what is this called? It's called bias?
Yeah, that would be the bias.
Yeah. And for linear regression, I think it's also the intercept.
Yeah.
This y equals n supposed to be, this term is the b.
Yeah. Yeah,
And so you could imagine it as like, all of these models have a bias. They all have a b. It just comes first.
yes, that makes sense.
So the value of the feature for that thing is 1. Right?
Yeah,
it's if you're multiplying by x0,
because that,
which is always 1.
that makes the
And it
multiplication
has some coefficient. 1 times coefficient is just b.
Yep. Yeah, and this like section finishes with like reframing the MSE. Mean square error, but reframing it in a matrix notation. I mean, no, not really. Like this is not the matrix form yet. This is just okay if we were to sum for each element of these two vectors. But we soon will be doing the same thing, normal equation, just pure matrix notation. That's it. Are we confused about anything else? Opening?
This is all review for me. So
it's slightly different actually. The MSE is like a cost measure. The normal equation is like an equation for finding the ideal parameters. The normal equation is what minimizes mean square error.
So the normal equation is just a closed form version of linear regression. I didn't like really dive in too much because it like doesn't scale at all. It seems like there's no practical use for it unless you like have a really like short time crunch or a small linear regression problem.
Is that much faster than gradient?
Yeah, well, it would be way faster for a small vectors.
It converges
like
most things can figure out.
Yeah.
They both converge.
Yeah, but this. Oh yeah.
I think you just plug it into the normal. I think it just like outputs the solution.
Yeah. But with large data sets, like the matrix operation was my interpretation. I think specifically the transpose. Many dimensions, but anyways,
I think it's the transpose times the original matrix.
That like
that's
operation.
Like a gigantic square matrix. It's when you transpose n by n, you get n by n times n by n. The inner m's cancel out and you get n by n. N is the number of features. And if you have many features, then this is like a terrible, like huge, large matrix to compute. Because you have to multiply every feature by every feature, essentially.
Like James said, it's a good like sanity check if you do have a small enough model to use it. And you're just like training linear regression, you can train with like just a small subset of your training set, and then just compare the results in normal equation just to check that. I guess just to bisect your or if you're debugging something, it's your model that has an issue or the training itself. So
that kind of covers computational complexity. I was just saying that.
Oh, sorry, yeah.
I mean, that's fine.
I can go next now. All right, cool. Gradient descent. This is an alternative to the normal equation that is a little bit more tractable with large numbers of features. It has a couple caveats, right? I mean, in the ideal case, your learning rate allows you to converge to a global minimum. But if you choose a learning rate that's too small, and you stop iterating once the norm of your gradient step is too small, the norm being like the length of that vector. And like the norm of a vector with 2 points is just like it's like the length of that vector. Same for many dimensional vectors. So once the norm of your gradient step is like very, very small, like less than some eta, which is like a trivial parameter, then you generally stop stepping. And if your learning is too small, then you're going to have very small steps, and then you might stop before you actually hit the minimum.
What was a norm again?
A norm is like the length of the vector.
So a small norm just means it's a short vector.
Yeah. And that's how you know to stop. Literally. I mean,
Your gradient. So if you have, because if you have a really small gradient,
it's like, okay, we're in a flat area of the loss surface, and so the gradient step that we're calculating is like not really in any particular direction very strongly, and then we multiply that step by like 1/100. Our learning rate might be like small, so we make a tiny, tiny step. And we substitute
the magnitude of your steps.
So when the norm is
what is the magnitude?
that's the magnitude of your step is like the length of the step. And that's determined by both the gradient that you calculate and the learning rate, because you multiply those two together to figure out where you're going and how far you're going in that direction.
Yeah, so basically you multiply like slope by like learning rate, right?
Don't think of it as slope, think of it as like a vector, which has like both length and direction. So when you're standing on a hillside, your gradient will be larger if it's like very steep, and shorter if it's very shallow. So that's a vector with length. And then you multiply that, or you divide that by 100, because your learning rate might be like 1. And so what you actually do is you take like 1/100th of that step. And the reason that you don't take too big of a step is because you might overshoot yourself. You might like land on the other side of a bow, for example.
Here I was like slightly confused because like if you have a function that you know is convex, you should be able to automatically recover because like, oh yeah, I took too big of a step because but now that like this the vector is pointing in the same other direction.
Right,
So
you just like bounce back and forth.
no, but see, like here's this like this figure for 5 shows you like going bouncing back between the sides, except it keeps going up, right?
So the vector here is like okay, so here's the cost and here's the step, right? So because the gradient is pointing this way, you make a step in this direction, right, parallel to the x-axis, and we end up like here at this point x, which corresponds to this cost,
And this
which is actually a larger cost, which is not what we intended. And so now the gradient is pointing into the left, right? And so we take another large step, larger this time because the gradient vector is larger because the slope is slightly steeper at that point, which corresponds to this x, which has an even higher cost, and now we're like diverging.
Right, but my question is because like this is like you cannot solve this for an arbitrary function, right? But if you know your function is convex, I think shouldn't you just immediately decrease your step size if you notice you're taking bigger and bigger steps? Because like you should expect that in the direction you're going, the slope should be getting less and less, more and more shallow.
I think that is something that people do is they decrease their step size. I think that is training.
Yeah, if you know that you're in a parabola and you're diverging, right, or you're taking larger and larger step sizes, then given that information, you'd be able to say like, oh, I should decrease my learning rate automatically.
Yeah,
that would totally work.
Yeah, but the solution people actually do is like, okay, just with each successive step, it will be reducing.
The reason people don't do this in reality is that there's an even better solution than that, which is a second order gradient descent. So when you normally calculate gradient, you're looking at the first order derivatives, right? If instead you look at the rate at which the derivative is changing, then you can take one step immediately to the opposite. And that's only possible in complex functions as well. And so there's other solvers, not stochastic gradient descent, that solve for this. There's one called the Newton's equation.
I remember the second order.
Yeah. So one way to do this with like more complex equation that you're trying to solve for is to like take iterative snapshots of the first order gradient, which are easy to calculate at any point, and then like watch how they change over time, and use that to approximate the second order gradient, right? Which is called, this one is called the Jacobian matrix. The second order is called the Hessian matrix. And with the Hessian, once you like get accurate estimates of second order derivatives, then you can take like much larger and more accurate steps.
Yeah,
which is cool.
So like you're saying, like, so in practice, like if you knew your function is convex, you would never actually use like the naive gradual descent because there are far better solutions to adjust for this automatically.
You'd maybe be like, okay, the derivative here is like, I don't know what this is, -2. but it's also decreasing at a rate of 1 every x, right?
Oh, yeah.
And so given that information, I know that the first order derivative will be 0 in about 4 units of x. I'm just going to skip 4 units of x to the right, where the derivative is 0.
Oh, nice.
Which is the middle.
Okay, yeah, thank you. I was
Wait, is this second order derivative always consistent with that?
So for this, yeah, the second order derivative is always right, because the gradient, the derivative here starts at -2, over here is -1, here it's 0, here it's 1, here it's 2.
It feels like, I don't know, that feels almost coincidental for this.
The second order derivative is like the rate of change of the change, right?
Yeah.
Like the acceleration.
Yeah.
Of change.
Yeah. Is that always? Is it like?
I mean, this
is always that.
This is an idealized case.
Yeah.
I think
I feel like there's
in this case you can take the perfect step. In most cases you can't take a perfect step. You
take
still
a better.
iterate. You take better steps.
And like you always, for the second order derivative to work for the level, you always want like a convex function which is like actually continuous.
Yeah. A lot of research is around like second order optimization methods, and like there are problems with them. Like they do get attracted to saddle points, which is one where the derivative is 0 if you look at it from this angle, but from this angle it looks like a saddle, right? You can still go farther down in the cost surface, right? There's like a lower cost down in this direction. The second order derivatives tend to get like attracted to saddle points, and so like introducing a bit of randomness to like jostle them out of that position can help. And then there's other fancy things that you can do.
I love that solution. It's like you can use it like
Add
so many
noise.
previous times for
Just randomness, yeah. Just wait a random amount of time
Just
and
wait
somebody
a
requests again.
Crazy.
It's true, it's all over the place.
Yeah.
I don't know what to do. Just to say random.
Speaking of which, if you're in a local minimum, sometimes you can jostle yourself out of that with randomness. And maybe you take a big random step over here, and now you're going to go over here.
It feels like something.
Another solution to this is like initialize yourself randomly so that you start in different places around the cost surface.
Oh, yeah.
Some of them will end up in better positions, like the global minimum. Some of them will end up in local minimum, but you'll be able to tell the difference because you can see that this cost is lower than this cost.
Yeah.
Here's an interesting one. So here are one feature on the y-axis, one feature on the x-axis. We can see how much the cost changes as we move our parameter for these features.
I think that has to do with different scaling.
Yeah. And so this is actually pretty unintuitive to me. So since feature 1 is the smaller scale of these two features, it takes a larger change along feature 1 to affect the cost function.
Yeah. Yeah. Like that, it hadn't occurred to me that was a benefit of scaling. I remember last time I had a question like, this guy got way better performance by just scaling inputs on what seemed like an already scaled like data set. Yeah, might be similar.
Yeah.
Would like an alternative be like basically what that's saying is that like one blanket learning rate is just affecting different parameters differently. So would an alternative to get that, like obviously more complex, but one alternative way to get the same effect be to have different learning rates per parameter?
Yes, absolutely. And this is a paper called KFAC. It was real things that we're doing.
Oh.
Yeah. So it is.
That's totally outdated.
If you remember something like how precisely is like having different weights. Oh yeah, okay. So I was wondering how is this different from, because if you scale your weight, right, it's slightly different. How is this precisely different from just scaling your feature values?
It's a similar impact. This might be, actually, I'm not sure if that's KFAC. There's a paper. Yeah, I think it. Yeah, I think it's maybe easier to like take a slightly more sophisticated gradient step than maybe to scale all your features in some situations. That's the reason.
Yeah. Also, I can see like if your features are not uniformly distributed, that would also help.
I've also seen like linear algebra solutions where they like transform the gradient space, the gradient step, into like a space in which the matrix that would normalize this space, you use that to transform the gradient step so that you take it's linear algebra magic. The effect is you take smaller steps in the y direction and larger steps in the x direction.
Yeah.
Cool.
So for these, so the two properties that are down for the cost function, MSE, that like allow you to do all these new things are that is convex and continuous. Is that like something you kind of just have to know? Like, would you just look up is my cost function convex, is my cost function continuous, especially in like many dimensions?
If it's not continuous, it's not differentiable. So like gradients would work.
Yeah, there's ways.
This is true. Yeah.
Your question is like, how do people know this about their costs?
Well, yeah, like I'm working on a problem, and I'm like, okay, this seems like a reasonable cost function, and like, how do I go from that to, oh, I know it's continuous, I know it's convex, and I can take advantage of that model. Like, is that just
something different? It's like when it's convex. I mean, you should take your. What would you do differently if it was convex? How would you change your?
Well, convex is good because that
choose a
means
better
you can get a you can get a goal there.
I don't know specific. I don't know how you do it in every situation.
Okay. I mean, if it's Googleable, that's fine.
A lot of times your cost functions are something like it's application specific, right? Like you can create a very unique cost function to do what you want.
Yeah.
So how do you do that?
I mean, let's say that you could also just plug in a bunch of random values, like pick a bunch of random, sample your parameter space, and then measure the cost of each of those parameter combinations. And you can start to get a sense of the shape of your off surface.
Yeah, but if you're wrong,
and
what happens if you plug in a convex function?
Well, it'll still find a minimum. Like the thing about convex, like the nice property of convex, at least from what I understand, is that there is a global minimum.
Yeah.
And so, like if you find that, then you know that you're on convex function. Then it just seems like
I mean, I don't even know how when I was having React. I think you would find a local minimum, right? At least. I think
if it's really non-convex, then maybe it looks like really bumpy. But you'll probably find something like. There's also points of like where spaces go like step. It's like non-differentiable. Like let's say that you land on the corner.
Oh,
you can't make any step. What happens then? I don't know.
Oh, that's a good question.
Random possibilities.
Cool. I'm gonna grab a.
Do you guys want? Are these heat lamps?
They're heat lamps. Yeah. Do you want to turn it on?
We can take a look.
I'm fine.
Bartosz right now. Here's close.
No, I'm saying I'm fine with being on the road.
I'll turn it on. Very cool.
Yeah. Okay.
You guys can keep going without me.
I'm on batch.
Do you guys have anything else on?
So yeah, so batch grading in the sense is like, okay, let's do everything just described, and yeah, like do it all the data in a feature vector, and that's basically what it does. Like it step based on like the derivative at the current point, and then you can take those steps. But the problem, at least the nice thing about batch grading in the sense, like okay, this is not like a total function. You don't have like n squared. Because you don't have to do these huge matrices and then invert them, because you just do it one step at a time. This faster when it comes to runtime. It still will always, I mean, unless you choose too big of a step, it will always converge. The problem with this is like, well, yes, but still for every step you need to look through your whole data set. You look through your whole training set every single step you take. So that's like the not so nice thing about it. But if your data fits in memory, this is actually not about solution. I mean, it seems like memory storage uses like batch to batch sense. So like a mini batch. Yeah, batch to batch. Yeah. Is there ever like a reason to use batch grades? I mean, it has nice properties. Okay, like it actually converges. Yeah. That's the super.
Yeah.
It felt like it was. Converge, right?
I mean, yeah, it felt like it was just. Like I feel like it's just a step towards the batch, or
I can imagine switching a batch once you get it close to a solution. We talked about that like
Yeah.
days.
Well,
Switch
Oh,
to
that's
that.
true.
So
I guess
the
if you don't
advantage
really
is
get a
that you
true gradient with
like
stochastic batch gradient, then you get like
yeah yeah that's
Or
true.
maybe like you don't even have to do the whole batch. You could just like up your mini batch size. Yeah, kind of cool.
Yeah, they probably do have like smart batch size features.
But like, so I think mini batch is like, there's not so much convergence that like will start bouncing around at every point.
Yeah, that's what you know.
But
yeah.
it's not. I don't think it's even guaranteed for mini batch that like, the bounces will actually get smaller.
You said it's not guaranteed that they'll get smaller.
Yeah, I don't think it is. I think
Interesting.
no. For batch gradient descent, I think it's guaranteed. For mini batch, I think it could just be flipping around endlessly. Yeah. If you choose your
Yeah.
inputs maliciously.
Yeah. That's, yeah. I think most of the time you would not use batch. At least you
Oh yeah.
Yeah, so stochastic gradient descent is basically the other end of the spectrum from batch GD, where you just take one random example at a time. The advantages are that it converges, and it converges much faster, and it's much obviously more scalable because you have to infinitely large data set. You're just taking one training example at a time. You don't have to put the whole thing in memory, and then it's also more random, so you can escape stuff like local minima. The disadvantages are that, like Bartosz said, it is not guaranteed. Actually, I don't think it can tell you if it's at the global minimum, or at the very least, it's not guaranteed to a global minimum. I think like even if you get to the actual global minimum, like the next example can push you out of it.
Yeah.
So there are ways to like address that. You could switch to batch GD. I think the book mentioned simulated annealing, which is reducing your learning rate to the point where you're making small enough steps as to become negligible. Yeah, does anyone have questions on that? I had a couple questions on this section to get into. So he mentioned that shuffling the training set and going instance by instance converges more slowly than just picking random instances from the training set. That was my question. So that the subtle difference there is if you just pick random instances, you have the potential for duplicates.
Yeah.
Whereas if you shuffle the whole thing and go in order, then you're not going to get duplicates. Okay. So yeah,
the shuffling going in order is better.
Shuffling going on is worse.
Worse.
I feel like I feel like if anything, because of like I feel like getting duplicates, you're always going to get less signal from the second time you see the same thing versus something completely different. So I would assume that would hurt.
Yeah, that's right.
Maybe I read it wrong.
No,
I don't think you always get less signal the second time you see the same instance.
Less signal than a completely instance.
Sure.
Well, I don't know.
That's not my intuition.
Interesting. I mean, I guess you would be at a different point in the. Yeah, but I mean, even still, I don't see how that would make it better to see something.
Yeah, I was thinking the expected value of picking a random thing and doing this, the number of things we're playing is like roughly the same as picking everything once.
Yeah. Another possibility I thought of is just the upfront cost of doing the shuffling stuff as time.
Oh, yes. Was it saying slower to converge in terms of actual runtime?
Yeah,
or
yeah.
the
Like the way he worded it was, I assume number of steps.
Yeah.
Did he say how much of a difference it was? Because this seems like so tiny.
Different games.
Something else to make it. Yeah.
Well, it does have an impact, right? But even like training any, unless it's specific to linear regression.
Well, like what would you use a stochastic gradient to say?
Well, even with mini batches,
the same thing.
Well, there's two approaches to mini batches. One is shuffle the entire thing and make a batch. Second is just pull 60.
So I guess
So, well, yeah, it seems pretty impactful if it applies to all gradient descent algorithms.
It's like a random selection with replacement, random selection without replacement.
Yeah.
Which?
Random selection with replacement is just what you think of when you with basic random selection. And without replacement is an upfront shuffle, and then sequential.
Right. So replacement means like you pick
put
it
it
out
back.
and then you put it back in.
Yeah.
And then you pick out a random one. So which one is better?
With replacement. It's better.
He said
Right.
faster. I think that's very
Converges fast.
I think he
You
meant.
want to read the?
Yeah. It says nobody sure you're gonna go through every instance at each epoch. Another approach is to shuffle the training set and go through instance by instance, and shuffle it again and so on. However, this generally converges more slowly. I think he meant the runtime. If we're talking about convergence, which doesn't really have to do with the algorithm runtime. I mean, although like one of the questions at the very end, he also was like asking like what is faster to converge, and he actually meant runtime. So,
It seems like rare that you talk about convergence in terms of like actually.
Yeah.
that's why I was
Well,
surprised on the question section that he meant runtime. So I think
Usually measured in like epochs.
yeah, like if I had to guess, I would guess that this. Like, one thing is to just try it out.
Yeah.
But yeah, I would be very surprised if it would make a difference in the number of steps.
Me too.
I mean, it seems like there's no way. Well, it seems like it's like the difference is almost negligible. But I was just really surprised. It seems like there's no way the algorithm with replacement should outperform.
Yeah.
What was your other question?
My other one's actually for just answering myself, but there's like a ravel method.
Oh,
that,
yeah.
Like flatten. I just thought it was funny. It's like I've heard unravel. I've never heard ravel. I was like, weird.
Would unravel be flattened?
Um,
Unravel would be like, I imagine a matrix is like a coiled up pile of string. You unravel it to a flat string.
I thought of, so if you have just I guess I thought of it the other way around. Like you're unraveling. I guess you're.
I've seen that name somewhere.
Or
Either some very weird scientific language.
yeah, it might
That
have
like
So ravel does mean flatten.
yeah.
Yeah, that would be fun.
Yeah, that's
I
interesting.
regret
Maybe-
explaining the wrong thing.
Well, yeah. Well, I'll probably get that mixed up from now on. But I thought that was just.
I bet. That was stupid.
Is that it for SUV? So I guess mini batch SUV is just kind of a combination of the two. I think that's the most frequently seen that people use. I guess one disadvantage of it is it with SUV you're going to be jumping around more because your gradients are kind of more wild and as smooth as when you're averaging. This is kind of just a middle ground between gradient descent and stochastic gradient descent and fast gradient descent. The one thing it does mention here, which maybe to your point, Bart, I was just talking about like duration, is that fast gradient descent takes like a long time each step. Yeah, like maybe it's not just in terms of like because that would be the difference from that is like stochastic gradient descent you can compute it like immediately to like one instance. Fast gradient you have to like do everything.
But I guess like, if you're actually trying to pick, you don't care about the number of steps. You care about the runtime, right?
Yeah, I guess it depends.
I mean, at the stage where you pick the algorithm,
Well, if you have way more steps, then that translates to one runtime as well.
well,
Yeah,
right. But
like
the
a lot of
method
steps could be like like a pipeline, you kind of bash a lot of the results in a lot of steps. So.
right, but within a model, like when would you care how many epochs did it take as opposed to how many seconds did it take?
But usually you see in paper and stuff in the reference ethics.
Well,
Yeah,
paper,
so
Yeah,
paper
way
should-
to
why would
like
you care like,
performance.
in practice?
I think
I think like number of epochs is just a more like transferable metric because runtime is dependent on your hardware setup and all that. So if you're trying to replicate the results from paper, you would look for the same results at this like you're trying to evaluate the model, like how the model itself is learning. So you would see like their results after 10 epochs. You won't be able to match that up. If they said the results after 2 hours, there's no way you could
Oh no,
exactly.
right. Like this makes sense
About some model size.
Yeah.
Yeah, like if you're comparing yourself to a different model, I guess yes. But if you're like doing things like in practice, like I need to run this on this thing and see what the results are. Like I don't invest epochs. I want to say I'm willing to invest 2 hours into this.
Sure.
That's a good thing.
Yeah.
What hardware?
But on my hardware, like so.
Yeah, no, I see what you're saying. So if you just work on your own project.
Like you decided probably that.
I would optimize for time too.
Yeah.
Training my own
So
models.
that's why I'm saying that he may be actually using this because, like, again, he's like seems like epochs are also mentioned as an afterthought thing.
Yeah, but I think it's more common, at least in my experience. In literature, you'll see epochs referenced.
Yeah.
But I agree with you. Like, if I were building a model, I would care more about how much time it's taking.
Polynomial regression. So with the linear regression, which is why I've told plus B before, polynomial regression is just adding another coefficient, multiplying that by like x squared, and that scales up to any number of features. Interestingly, the scikit-learn implementation will also compute all combinations of features up to the given degree, such as, so for degree 3, it would also compute a squared, a cubed, b squared, b cubed, and a squared times b and ab squared, as you said.
Yeah.
And even though it said that, I didn't see those coefficients in the polynomial features coefficients here on the top of page 122. So like, if it is computing those coefficients, then where are they? I didn't see them on this. Which right? So one of these is going to be.
So this is above which graph?
This is 122. This is like up above 413.
Okay.
Is the capture the 412?
It's between 412 and 413. It's a code snippet.
Oh, okay.
So just below 412. So like, where are the coefficients for A times B? This is x squared x, or maybe it's because there's only one.
There's two things here, right? Like there's a normal linear regression right above the graph. That will not take features. Okay. And above that, right, you have x poly, right? Is that the
X poly?
Yeah, like which is,
I mean, I think it's just
I was confused by this little note over here at the top of page 1.
well, yeah, but versus which piece of code?
This piece of code. I would expect like there to be other terms of combinations. Oh, you know what? It's because this is this has one feature, and many like the feature squared, the feature, and then
Yeah.
the feature. When he said polynomial features with when it includes features like two features, one feature A and one feature B, then fitting a degree 3 model to those two features would result in all combinations.
Yeah, degree 2 should also have A times B, right? But there's no B.
That's because you didn't include the bias.
Oh, so if you include the bias includes combinations.
Well, then you introduce the third parameter. Sorry, the third feature.
I think the bias is the intercept.
That's what I thought too, but it seemed like
different.
it seemed like it didn't include the combination.
Oh, the features. When you say A and B,
So like here you only have one feature, right? That's called feature A, right? So if you do a second degree thing, you kind of like you combine A with A already because you did A squared.
Yeah.
But if you get A and B, you would have seen a bigger thing.
Yeah.
You would have seen A squared, B squared, or you could have seen A, B, A squared, B squared, and AB.
Okay.
Yeah.
I think I've got it now.
Yeah.
Okay. So what we have here is a one feature model. The only feature, so this is figure 413. The only feature is X.
Yeah.
Right? And Y corresponds to the cost.
Yeah.
Or like a predicted, like the label and the score, whatever. Not the cost.
Predicted value.
So the line of best fit through all of these points on this XY graph is just some combination of coefficients for X squared, X, and maybe an intercept, although this one looks like it has no bias, which I think needs no intercept.
Are you sure the bias maps directly to the intercept, even for, yeah, I guess yes. Even for polynomial, it has to, right? Because it's just x equals 0, so all the other features are 0. Or sorry, all the other features are 0, and then the bias would be the intercept.
Say that again. I think you can make figure 413 without an intercept.
Without specifying an intercept. But
where the intercept is 0.
Figure 413.
Yeah.
So if you had a bias of 2, then the intercept would be 6, right?
Why do you say that? Oh, because there is an intercept.
Oh, sorry. I thought it ended. I thought the bottom left.
Yes,
sir. The intercept would be like 4. Like the y-intercept with no bias is a little, or like around 2, right?
I'm confused by the difference between the y-intercept and the bias.
No, okay.
Right. You were saying they're equivalent.
Where is the bias?
You don't think so?
No, because there's no bias in this model, but the
so
intercept is
I
not
see
0.
I see that it says include bias equals false.
Right.
And then you also, if you look down, you see the lin-reg intercept has a value of 1.78.
Right.
Oh no, so what? No, so for the very first thing.
Oh, but the second one is a different model.
No, the first one is
it's just fitting.
The first one is not a model at all. The first one is just transforming the features. And you say, I do not want to include bias as a feature of mine. That's why you only have like x poly is everything that was transformed, right? So we have x, now we have x and x squared. That makes sense. Those are your new features. So features do not include a bias term because why would they? And we asked it not to.
Okay.
And then when you actually run the model on it, you have intercept, which is the x0 thing, and then you have the array of coefficients for your two new features.
So bias is pre-training. Intercept is post-training.
I think like bias is a thing you could include, but I don't see why you would.
Okay, that's what you're saying.
Yeah. So
you multiply the features together. When you include bias in the feature set, it multiplies them together, right?
So x poly is graphed in figure 413.
Actually, we can really check what the bias thing is supposed to mean. Sci-fi, right?
A scalar.
Oh, actually, it still found it. Yeah, so include bias is a little like this. Like it either includes a column with each polynomial of power 0 or not. So yes, I don't see why you would want this if your model already does this by itself.
Yeah.
Does that resolve the confusion?
I think I was confused about what these systems were doing, but we can move on.
Okay, so learning curves now. This is actually kind of an answer to a question I had the other day, which is like, okay, how do you do this in practice? So yeah, and learning curves are a way, like you picked a way to evaluate the models. In this, it's RMSE. So that's what was optimized for. And then what you do is make a nice plot of like how, what's your mean squared error on the training set, and what's your mean squared error on the test set, and then you
It's a validation set.
on the test training set and the validation set, yes. And then you plot this over the training set size, because the intuition here is that okay, you want to prevent overfitting or detect that you're underfitting. Varying this over the training set size will not usually let you detect overfitting real quick, because okay, as you included too many samples, okay, you overfit to those, but then your performance on the validation set will just take a plummet. Okay? And here it was two nicely converging lines, yeah, sure. But in practice, if you do this wrong, you would see like the validation set line on figure 415. If you go wrong, it would just start going back up. And here, it was kind of weird that there was no example that does that. Okay? And yeah, then there was like then there was like this discussion of bias, variance, and irreducible error, which like I wasn't exactly sure how does that work. If somebody knows, I would, because like okay, bias is the part of error due to wrong assumptions, and variance is for small variations in the training data.
Cool. But what do I do with this information?
I think it just has to do with model complexity. So when you're choosing a model, those two things are inversely related. So if you increase, like if you choose a more complex model, then you're going to make more assumptions. Well, you're going to be able to cover like more ground and like fit your models more closely to the training data. But by doing that, you're also making a lot more assumptions about like the test set, and some of those are bound to be wrong. So more complexity means increased variance and reduced.
So the thing that is specifically varying a lot is the parameters of your model.
Yeah.
If you have a slightly different training. Like let's say that you have one large bunch of examples, and you choose subsets of those examples and make like 100 different training sets.
Yeah.
Right. If your model has 10 degrees of freedom because it's like a huge degree polynomial, then that's going to be a high variance model. Because for each of these subsets of training data,
If I arrive at a
the coefficients are going to be totally different, right? The coefficients are going to be different.
Right, so if you choose a more complex model, you reduce bias, but at the cost of increasing variance.
Variance of the coefficients, yeah.
Okay, that makes sense.
Likewise, like a high bias model, like linear regression, right? Let's say you have some real bendy data.
Yeah.
You choose linear regression, so you only ever fit a line like this. Even with totally different subsets of data, you're going to have like pretty low variance in coefficients. But you're always going to fit a line that's like pretty much, half. Slope is 1/2, intercept is 1. But your error is going to consistently be large.
Yeah.
Right? That's attributed to bias.
That makes sense.
And then there's like
so there are ways to kind of deal with the bias variance trade-off. One of the most common ones is regularizing models, which basically means discouraging large model weights, because large model weights will lead to a lot more bias. They'll like give you weirder predictions, basically. So ridge regression is what's called L2 normalization, where you penalize the model based on the sum of the squares of all of its weights. So you can use hyperparameter alpha to kind of control how much that happens. And the more regularized your model is, basically the smoother it'll be, and the less it'll try to like reach and get an example that's a little bit more high.
Regression is L2 norm, right?
Ridge is L2.
It's a squared L2.
I thought L2
That's
sounds
L2.
good. L1 is just the
L2
sum
norm,
of
I think,
weights.
is the square root of all of it squared. L2 norm is like equivalent to the Euclidean length of your vector.
Yeah.
So like
This is the square of a
so you guys, it's related to the L2 norm is like the Pythagorean theorem. Right?
Yeah.
Like to get the hypotenuse of a triangle, square x and you square y, and then you take the square root of the sum of those things, and that's the length of your hypotenuse. Yeah. L2 norm is that process for any number of dimensional vectors. This is a two-dimensional vector.
I just thought this was L2 norm. Something else.
The difference between getting the hypotenuse, getting the length of the vector with L2 norm, ridge regression is that ridge regression
is the square
additionally
of L2 norm
squares it,
basically.
which cancels out the square
Yeah.
root, which is just the sum of all squared coefficients.
Yeah.
Be like a much
Which is
larger-
computationally simpler because you don't have to
I
have
see.
every coefficient squared. before
Oh,
you
but
get
it also
the
has
Oh,
to
square
converges
rooting.
to the same thing, right?
But yeah.
So L1.
Whatever converges to the square root. Yeah, it's mentioned that.
So then what's the L1?
The L1
L1 is
is
the
next one.
absolute value of all the terms.
L1 is last regression, right?
Yeah.
So
So
L1 is just the coefficients.
there's no
you don't square the
squaring?
coefficients.
okay. And then L2 is the square root. No, L2 is just the squares, and then ridge regression is the square root of the squares.
No, the other way around.
Other way around. Yeah. So L2
L2
is
is
the
like
square
getting
root,
the Pythagorean. L2 is Pythagorean.
which is the squaring.
Where you square the coefficients and add them together, and then you square root the whole thing.
Right.
And that's the length of the hypotenuse.
Okay, and then
ridge.
is adding a square to the entire
Thing, yeah, which cancels out the
I see.
square. Yeah. And also, it's 1/2 of that, I think. So, yeah.
And also one, who knows why?
Yeah. Well, you have the alpha.
The lasso regression is next. It's basically just called one norm. But one thing that was pretty interesting that I didn't fully understand is the fact that it like basically does feature selection for you, just like tends to weights towards 0, which that don't matter. That seems super useful, right? Like it seems like well, this penalizes outliers less, so if you have a lot of outliers in your data, I would want more good. Also just seems like very useful in the fact that it's just feature selection for you.
Yeah, lots of
I didn't realize I used it.
I've used it before. Yeah. This graph helped me understand how it does that. I saw a YouTube video of like Rob Tiptroni explaining his invention because Rob Tiptroni wrote the very first book on statistical analysis, which I covered back then. But I think the way I think of it now, having looked at 419, is that it sort of like twists the cost surface towards one of the axes. You know, along one of the axes, one of your features is going to be 0. Sorry, one of your coefficients will be 0, right? Along the x-axis, the y coefficient equals 0. Along the y-axis, the x coefficient is 0. And you can see how the lines of the cost surface have sort of like twisted such that descending the cost surface quickest takes you straight to one of the axes.
This one is last size.
Yeah. On the right is lasso, and you can see how they like have these points, these angles that touch the x-axis, right? Whereas without lasso on the left, they're like nice and smooth, curved, and so there's no additional incentive to like be anywhere close to the x-axis on the left. But on the right, if you follow the dots, the fastest way to descend the cost surface goes right to the x-axis, and then it sort of sticks around there. It's like this cool, I would expect magical and like unpredictable quality about lasso. That turns out to be very useful.
I do have a question for you. Lasso ends up looking pretty good because, well, you know, luckily our global optimum is handily close to the 0 line, but if it's not, like would lasso still perform as well? Like imagine if you know the optimum was actually somewhere way up in space. Like you actually do need both coefficients.
Yeah, I think it would still get there. Yeah, but for very like high dimensional spaces, a lot of them can be zeroed out.
Yeah,
which no.
You should just do like a polynomial regressor with like very high degrees, and these lasso regression and have it like.
That's essentially what we're doing at Sorceress. We have like all these keywords that we need to get their features to be 0.
Well, it's not polynomial, more parameters, not more features.
That's true. Oh, we will add more features, right? Because it'll combine features in different ways, right? You just have
that's right.
like them like.
Yeah, so you can just do that and just like let lasso sort it out.
So this quick section on elastic net, which is just a mix of the two, which must have been the easiest paper ever to come up I like the practical tips here. So ridge is a good default. If you suspect that a few features are actually useful, then you should reach for lasso instead. In general, elastic net is preferred over lasso, since lasso may behave erratically when the number of features is greater than the number of training instances. And I'm not exactly sure why that is. Or when several features are strongly correlated. For that last bit, do know that the lasso will randomly choose between two highly correlated features, which one it selects, which one it zeroes out. Not very loud there. I guess maybe the ridge will even that out. Because ridge tends, so for ridge, if it's got two strongly correlated features, it tends to flatten them both towards 0 about proportionally. So maybe combined with lasso, that's like a moderating behavior.
So like if you get two super correlated features, like ridge would say, oh, there's some signal on both of those, and basically half of the signal. Lasso would be like, okay, I'm going to, you get it, you get all the signal.
Exactly. Yeah.
That's your best feature.
Yeah.
Yeah, that makes sense.
Well, in computer science, we have a hybrid approach.
Yeah, and after all, we get early stopping, which is kind of inadvertently discussed before. discussing is skipping two sides of the thing, except this is applied to just your root mean squared error on the validation set. Because the nice thing is like if your function is convex, so then whenever you're near you can be near an optimum, or you can be moving near to it or moving away from it. There are no local optimums to something like that. So if you found a good thing going, that's where you should be, and that's what's the nicest criterion for early stopping is, which is to say, okay, once our results start getting worse, we should probably just stop. Except in practice, when they said like, okay, no, you should not stop immediately because, for example, batch gradient descent would oscillate around the optimum for a while before it actually did it. So it might get in a good spot and then leave it immediately. Sorry, it might end up in a spot that looks good, and then it gets worse. But that doesn't mean that it's actually leaving the optimum location. That just means it might have been random. So for whenever you're trying to use this stopping criterion with models which do not strictly converge directly to the optimum, you should basically, like what I say is like, okay, when you're doing this, okay, when you think you found the best solution so far, okay, save it to the side and then run a couple of iterations still, because usually you will beat it with a couple of iterations still. Yeah, that was it.
So logistic regression is another type of regression based on the logic function, which basically takes an input x and scales it to, it pushes it towards 1 or 0, basically tries to make it true false by using the formula p or x log x over 1 minus x. So to estimate the probability, you apply this sigmoid function to the dot product of the transpose of your parameters and x. Yeah, that's it's just another form of regression. But the introduction to it is basically this is how it makes predictions using log function.
So it's training super log loss, right?
Yeah.
I've seen the log loss like a million times. What is, I know it just takes some probability and gives you some numeric value, but why is log loss so significant?
It's just you could think of it as like, I know it doesn't seem simple when you read it, but like it's the simplest, dumbest way to penalize the incorrect prediction. So like, let's say that the label is either 0 or 1, because we're talking binary classifiers. Right? Let's say that you predict, 0.5 and the label is 0. Well, if you take the log of 0.5, then you're going to get some like medium small number, right? I think it's like 0.3. However, if you guessed 1, which is like really confident, and the label is 0, then the log actually it's the log of 0. Sorry. The log of 1 and 0. I forget how you combine things in logs, but the penalty becomes infinity, which means it penalizes like the exact incorrect guess with a high confidence, which is really what you want.
I think
it does the inverse as well. If you guess 0 and the label is 1, you also get infinite penalty.
So like penalizes wrong answers a lot. Penalizes like winning answers like that. Yeah. So if it's like not very sure, to like do something better, something to get penalized.
And it's like a pretty good low penalty for like moderately correct answers.
Yeah.
I mean, you could have any function with those properties would have been an appropriate function. It just happens that people use logarithms.
Log loss is just like ubiquitous loss function.
Yeah. And the reason is it's like very simple.
Yeah, it is.
This was the.
Oh, nice.
Yeah. So like, x to what power equals 0? Well, negative infinity. Decision boundaries. So what's going on in this chapter? So there's an iris data set, which is like a famous classification problem. And the author plotted out decision boundaries given any combination of features. Turns out the decision boundary is binary classifier and it's linear. With one feature, it's just like two features, it's like a diagonal line. And and it's going to approximately divide the features. I think he was just trying to show that it works. It was a little annoying that the parameter for regularizing logistic regression isn't alpha, like with other linear models, but it's inverse C. That's just unbelievable.
So
The regularization parameter isn't alpha, it's like the inverse of alpha. So the higher the value, the less regularization you get for C. Whereas the higher for alpha, the more regularization you get. It's like annoying. It's like a little gotcha.
Yeah, and after that we have softmax regression, which is kind of a way to get linear regression to be to let you pick between multiple classes, but they need to partition the class space fully. So later on the questions to us like, okay, what if you had a thing which decided for rainy versus sunny and day versus night? Well, you could not use softmax for that because then you have 4 classes for which they're pairwise exclusive. So yeah, you wouldn't use it for that. But if you have just, for example, 3 kinds of flowers, so I have to do it here, it didn't work. What I was slightly confused by is like, okay, so they start for, okay, softmax store for class K is actually what, just a parameter? Yeah, like, can somebody tell me what exactly is said in equation 419?
419.
Softmax score. So
Well,
so K is
the class number.
the classes, right? So capital K is like the total number of classes, and each K is like the class.
Oh, and then
T is transpose.
okay, yeah. So it has like a matrix of linear regression models which are operating at the same time, kind of, and then like just picks one vector out of that, and then multiplies it element-wise with your. Sorry, and then there's like a product of your feature vector,
yeah,
and the vector of the thing that you're trying to predict, right?
X is like an
instance, or X is an instance vector, right? So that's a bunch of features. And then I think this transpose thing would actually translate to, okay, you have a matrix of these things.
Just a way to multiply the 2
pick out your own vector, then transpose it, and I can get those 2 things together.
Yeah.
Okay, that makes sense. But yeah, and because then like 420 makes perfect sense, because then it's like, okay, just how do you combine multiple predictions like this, right? Yeah, how do you turn them into a probability? Yeah, and that makes sense because here you like use exponential function, because like what the softmax function and what the softmax score gets you is not a probability in and of itself. You have just a bunch of numbers, and those are different numbers for different classes, so you need to normalize them into like one thing and turn them into predictions. And that's what equation 420 does, which is like you divide the x of your own thing divided by the sum of all the others.
So 419 is like, okay, for this training instance, I'm going to output some number that we're about to scale into probabilities, but these are like a preliminary number for each class, right? Larger ones are like a higher likelihood of this class being true. Smaller ones are less likelihood of this class being true.
But it's completely unscaled.
Yeah.
You have no idea.
And then we apply the softmax next, and then it scales to probability.
Yeah, and if you move the exponential function, like from equation 420 to 419, okay, let's define this case slightly differently. It will be super easy. It's like, oh yeah, now we just divide the thing. Like, okay, that's a probability. I'm not sure it's like how that is a probability, but I guess it will be between 0 and 1.
Yeah, it's sort of fuzzy whether that's like actually a probability. But
yeah, it's like a number that we call a probability. I was very fuzzy with that.
Because that's softmax looks suspiciously like the formula for the total probability of partition set.
Oh.
Really feels so good.
Oh.
Yeah, I don't know how to say it in English either. No, that's the worst about learning math in Polish. Yeah, that's like, okay, I did just kind of explain, okay, this is the argmax of that, because like, yes, you have a, like, we just defined how to get the probability for a given class. Now it's like, oh, now which class is it? Yeah, we do the argmax thing, which is like, yeah, we plug in the classes and find the class for which the probability is highest, yes, and that's a prediction, basically.
Yeah, I think generally there'll just be one class that will stand out.
Yeah.
Like you won't be between like 33 and 32%, or 0.3
yeah.
0.2.
Yeah, so that is actually best illustrated by like the very last figure is like, you know, the whole feature space partitioned into like 3 sections. And here you see like, yeah, but actually there is one specific point where they all meet. And if you happen to have a sample there, it's like, dude, I don't know, 33% exactly for each one of those. Yeah. But yeah, most of the time it's like, yeah, but outside of like that specific point, it's like, yeah, you're always, yeah, pretty much, you know, like there's a couple of lines, and one of the intersections, like, yeah, there you're really not sure between the two usually, and there might be one point where I'm not sure between any of those. But this is just like literally points and lines on the plane. This will not happen to you in practice.
Yeah, because probably your training process will move that 3-way point away from the training.
Yeah. Yeah, like if you had,
unless it really is like a really ambiguous zone where it could be.
Yeah, yeah, but if you had like just one example there, like it would not naturally move it further away from itself. Yeah. Unless your data is ambiguous, you would not run it. And again, like if you actually ask softmax to predict something, like yes, there are like, you know, right near that 3-color crossing, there's a zone that might say, okay, 30 for this, 20 for this, whatever's left for the other one, right? So then they will be close, but it's like, it will always actually make a decision unless you will that one single point. And yeah, that was softmax.
Nice.
I was slightly confused about what cross entropy exactly means, because this is just like
it just wraps another sum around log loss. So the sum over all the classes.
Oh, okay, yeah, okay. That is actually, yeah, that is a way better way.
The term, the sum from k equals 1 to k. Like
oh, we're looking at 422. Yeah. Okay. Yeah.
422. Yeah.
Yeah, I got it.
So if you just take out all the k's, just the log loss, or replace the k with 0.
Right. Or replace the y with 0.
Yeah.
Any other questions?
I don't know if I rage energy for all that stuff.
Yeah, we've been doing this for almost 2 hours now, so.
Oh, nice.
We don't have to do questions.
Yeah, I mean, unless you guys have specific exercises. The exercises are more just, at least my experience with them, they aren't super difficult. It's just kind of review.
Yeah.
Yeah. Did anyone not do the exercises to themselves?
I just did the 2 down.
The only thing, like, so in the exercise there is this question 7, which asks like, okay, which will reach the optimal solution the fastest? And I was like, okay, so
I have exit time.
yeah. No, and then I like was okay. So here's my answers. I turn to the end of the book and like see, okay, did I get it right? And for this one, it's like, oh no, we actually meant time.
Like runtime.
Yeah, the fastest is in the runtime. So like, they're cool.
Well, that makes sense because that distinguishes batch descent.
Yeah.
From all the others.
Yeah.
But I don't know if there were no surprises in there.
Yeah. Cool. Let's talk. For next one, the next thing on the agenda was for this week was supposed to be the text prep, like text data prep.
Yeah, I think, at least me personally, I don't know if you'd be able to like do other more guidance around, because right now it's just basically read the docs.
Yeah. So yeah, I need to actually like put together a concrete list of things to do. Fortunately, we can't really meet in 2 weeks anyway because that would be Burning Man.
Okay.
So why don't we meet in 3 weeks, and in the next 1 week I'll put together like the best time for next week, for the next unit.
Cool.
So we'll just take this week off, and I'll put
man study.
Oh my God.
Good
Who
one.
are you on this?
What?
You have like group buddies like that?
Sweet.
I'm at poker friends.
Oh, cool. Yeah, that seems more of a natural.
Yeah.
Yeah.